Look at this for a second. I swipe my finger across this cold piece of glass, and it instantly plays a video or sends a message across the world. How does a dumb slab of metal and glass physically know how to process those commands? It knows how to do that because it actually has a brain. Obviously, it's not a biological one. Our modern devices rely on microscopic materials that act like digital neurons. We call them semiconductors or microchips. But how do they actually think? It comes down to basic physical control. A semiconductor acts like a tiny gatekeeper. On command, it can completely block the flow of electricity or open up and let current pass through. When you flip that microscopic gate open and closed billions of times every single second, that incredibly fast switching pattern translates raw electrical current into the complex digital actions you see on your screen. That simple switching mechanism has to be happening far beyond our phones. Exactly. Those invisible switches are the hidden workforce running 5 massive areas of our daily lives right now. We moved from physical machines powered by gears and steam to an entire civilization running on microscopic switches. It is the foundational language of the modern world. Let's start with the device in your pocket. Instead of relying on a single generic processor, a smartphone uses a system on a chip. Think of it as a tightly packed, unified brain, where different sections handle entirely different tasks simultaneously. For example, when taking a photo, specialized chips inside the image sensor capture the incoming light. They instantly calculate exactly how to convert that physical light into millions of precise digital pixels. Right next to that, dedicated power management chips actively monitor the battery. They regulate the flow of electricity during charging, making sure your device gets the exact power it needs without overheating or failing. This same logic scales out to your house through the Internet of Things. Affordable, low-power chips are embedded inside everyday items. That is how a smart thermostat senses ambient temperature, learns your daily schedule, and communicates with your Wi-Fi router. Embedding these localized digital brains into ordinary objects turns passive wood and drywall structures into active environments that observe and respond to our physical habits. Moving from the home to the highway, the scale jumps dramatically. Older cars operated on purely mechanical parts. Today, a modern vehicle requires anywhere from 1,000 to over 3,000 microchips to function. They are computers on wheels. Those chips operate the vehicle's reflexes, known as advanced driver assistance systems. Tiny computers process heavy streams of data from radar and cameras in real time, triggering automatic emergency braking far faster than a human foot ever could. If you drive an electric vehicle, a specialized semiconductor material called silicon carbide comes into play. It manages the high-voltage power conversion from the battery, which directly dictates how fast the car charges and how far it can drive. But what happens when the math gets truly massive? Standard computer chips, known as CPUs, process tasks sequentially, one single step at a time. For complex artificial intelligence loads, that approach is entirely too slow. That brings us to specialized AI processors, designed for parallel processing, executing thousands of mathematical operations at the exact same moment. This massive processing capability is why generative AI can analyze human inputs and generate complex responses in real time. If we had to rely on the sequential processing of older chips, modern AI and autonomous safety systems would take days to make a single decision, rendering them completely useless. This high-speed processing also saves lives. In healthcare, specialized chips inside modern MRI machines capture raw sensor data and instantly calculate it into highly accurate, three-dimensional visual models of the human body. On the opposite end of the size spectrum, you have ultra-low-power microcontrollers. These allow implants like pacemakers to operate safely inside the human body for years, all running on a single tiny battery. Okay, we know what these advanced brains do, but physically, what are they actually made of? Surprisingly, they start as common sand. The primary material is pure silicon, extracted from the sand, melted down at intense heat, and grown into massive cylindrical crystals called ingots, which are sliced into perfectly thin wafers. Inside incredibly strict cleanroom environments, those wafers undergo extremely precise etching processes to carve out the billions of microscopic circuits that allow them to think. We take one of the most ordinary, abundant elements on Earth, sand, and meticulously carve it into the most sophisticated computational brains ever created. When you look at all of these systems together, the reality becomes clear. Semiconductors act as the invisible engine supporting the weight of modern civilization. If these tiny chips vanished, the consequences would be immediate. Global communication networks go dark, and hospital monitors fail. Even our transportation systems would freeze, not because the engines are gone, but because the digital systems that manage fuel, navigation, and safety would no longer be there to guide them. Every time you send a text, process a payment, or rely on a green light at a busy intersection, you are relying on the successful operation of these microscopic materials. So the next time you pick up your device or step into a car, take a second to recognize the billions of invisible gatekeepers working in the background to make it all happen. As we look toward the future, many of the tools we'll use to tackle global challenges, from climate modeling to developing new medicines, will depend on how much further we can push the limits of the semiconductor brain.